Chapter 8 deals with how we can deal with nonlinear relationships using multiple regression techniques. We know that multiple regression is based on a linear model, but we also know that not all relationships are linear. So in the OLS, the ordinary least squares regression, our B values are regression coefficients, reference slopes, which are straight lines that go through, plot through the data, a best fit line, right? That least squares line. While we say that the model is linear, it is actually linear for those slopes. So it is a linear slope line. It doesn't mean that the actual relationship is linear. It just means that we are plotting a linear line through it, a linear model through it. The model doesn't necessarily have to be linear itself in the x's, but we have difficulty with interpretation. So there's some techniques that we are going to talk about in this chapter to incorporate nonlinear relationships into regression. And there are several reasons why we might want to make some manipulation or mathematical transformation to our x's, to our independent variables. First, we may have some reason to expect that the relationship follows a mathematical form that is not linear but can be better estimated using something other than a line, straight line. Graphing the data may suggest that the relationship is curved rather than straight, and so that may give us a sense that we might want to try to find another model to use. And so we're going to talk about the transformations that we can use later on the dependent variable, but we're going to focus on those related to the independent variable in this chapter. So we're going to look at exponential models, logarithmic models. We're going to look at polynomial models, and we're going to look at dummy variables and how we can make those transformations to get better estimations of the data. So what are logarithms? The log of a number, the logarithm of the number, is the power to which a base is raised, to the exponent of the base, to get to a number itself. And it is the inverse of exponents. So I found this table, which I thought was a good illustration of this on a website about explaining what logarithms are. So if you have the exponential form, b to the x power is equal to y. The inverse of that is the logarithm. So the logarithm of b, the log base b of y, is what you get to x. So what does that really mean? So keep in mind that whenever you're looking for a logarithm, you're looking for an exponent, or the number that tells you how many times that base number is multiplied. So if 2 to the 4th power is 16, then the log base 2, so that would be our b, our log base 2, of 16, which is our y, is 4. 4 to the power of 2, you get 16. In its simplest form, the logarithm answers the question of how many of one number do we multiply to get to another number, okay? And so just getting your head around that. So 2 to the 4th power is 16, so the log base 2 of 16 is 4. So it's how many times you have to multiply 2 to get to 16. Right, or how many times you need to multiply 4 by itself to get to 16, excuse me. So the natural logarithm of a number is using the logarithm using base e, which is Euler's number, and it comes out to 2.71828. Don't ask me why, it just does. Is how many times we need to use e, right? So then now you have your base e, to get to a desired number. So some examples, the logarithm of 7.3, the natural log of 7.389 is about 2, because you have to take 2.71828 and multiply it by itself twice, to get to something close to 7.389. And the natural logarithm of 20.09 is about 3, because the natural log cubed is 20.09. So logarithms provide the basis for addressing issues with exponential curves. And exponential curves just mean curves that have exponents. And what we know about exponential curves is that the number of bends in that curve is equal to the exponent minus 1. So if something is squared, there's a single bend in it. If something is cubed, there are 2 bends in the curve. So it may go up and then down again and then back up, right? So up and down and back up. So the number of curves is equal to our exponent minus 1, our k minus 1 is the way that I was taught it. So we can use the logic of logarithms to perform transformations to our independent and our dependent variables that allow us to represent the curvilinear nature of the relationship between variables. The most common transformation of a dependent variable is to take its logarithm, to take the log of it. Why would you do this? Well, first, there are some variables like salary or time spent that are never negative. And when you log something, you can never have, it forces it to always be a positive number. And so that becomes helpful. Logarithmic transformations also guarantee that regardless of the values of the b, where the x is predicted value of y, it will always be a positive number. So you will always end up with that positive number. It's also useful for skewed variables because it forces a more normal curve. And I'll show an example of that in just a second. Some nonlinear relationships can be partly straightened out by transforming existing variables using logarithms. One way to do this is to take the natural log of a variable and it linearizes a nonlinear relationship. But it can also give us a pretty useful interpretation. So in this example, we can see that as x increases, y increases, but it increases at a slowing rate. So you kind of see that it goes really fast, but then the larger x gets, the slower y increases. But imagine if we tried to fit a linear regression line to this data. This might be the best that we could do. So a curvilinear regression line would be far more useful in trying to approximate what's really going on in our data. So a linear model is assuming that the change of x results in the change of y in a constant way across all values of x, and that may not be the case. So that's why we would want to use exponential polynomial logarithmic models instead of just a linear model that gives us a single straight line. So let me show you an example about this forcing it into a more normal curve. And this comes from a website from Ken Benoit. And so this is the relationship between, this is a histogram of expenses. And so you can see most people spent very little, but there are some people, there are these really large skewed values where people spent a great deal, right? When we take the logarithm of these values, we end up with a curve that is far more normalized. And so it addresses some of that skew and it squishes out some of that skew. It kind of normalizes that curve. So we can see a far more normal curve by taking the logarithm. And we like normal curves. Normal curves allow us to, move forward on all of those assumptions, right? That we assume that normal variation. So there are a couple of types of logarithmic models. Log-log models, which are sometimes called double log models, transform both independent and dependent variables. So both the x and y are plotted on a logarithmic scale, converted to logarithms, to provide, this can provide more useful interpretations. When we use the natural log for both x and y, the coefficient b ends up telling us the percentage change in y for a percent change in x, with all else being equal. So with all those, with everything else controlled, right? So it allows us to talk about percentage change, which is when you're doing a linear log or a semi-log, then you have unit change and percentage change in the interpretation. So the interpretation of a linear log where only the independent or the dependent variable are logged, but not both of them, then you have a percentage change in Y that is associated with a unit change in X, all else being equal or everything else under, being controlled. So the interpretation is a little less clear when we have logged only half of this half side of the equation, one side of the equation, but not the other, or an independent, but not the dependent, or the dependent, or not the independent. So you can see the value of doing a double log in that it provides for a consistent transformation. The problem comes in when you have some variables in your equation, in a multiple regression equation. Some of them can be logged, but not all of them. And so you just have to be very careful about recognizing which one of them represent unit change and which of them represent percentage change. So Allison gives the example of income and schooling. If we take a logarithm of income, which is a skewed variable, obviously, there are some people who are very far out on the positive end of that curve, right? It's also a value that can never be negative, right? You can't have negative dollars. You can't have negative income. You can have negative net worth, but you can't have negative income. The lowest you can have is zero money coming in. So we can take the logarithm of income and create something that is more easily interpretable than just having it in dollars, when that number, those coefficients are likely to be super tiny. So to run a logarithmic model, there's a simple transformation of the coefficients. So once we run the log, we have to make an interpretation, a conversion of the coefficients into percentages, because it's not given to us that way. For interpretation. So we take the log of our coefficient, right? So our coefficient for schooling is 0.094. So we would take the log to the exponent of 0.094 for schooling minus 1 and then multiply it by 100. So E is our natural logarithm base. It's that 2.7, whatever I said it was. I can't remember all of them. So for schooling, when we run this conversion, we end up with 9.9%, which tells us that each additional year of schooling, because schooling wasn't logged, so each additional year of schooling increases someone's income by about 10%. That's a really useful interpretation, and far more useful than saying a certain number of dollars. Because at the low end, that certain number of dollars means a lot. At the high end, that certain number of dollars may not mean as much. And so that 10%, for each additional year of schooling, we have about a 10% increase in income. That is a really useful interpretive structure to have for the relationship between those variables. Logit transformation is when we have Y as when we use our dependent variable, as a proportion. So we can transform the logarithm of odds into a probability by using the formula that Allison shares on page 155. So suppose that you have a sample of US cities and the proportion of registered voters who actually voted in the last presidential election. So you could run this proportion of those who voted in the election minus those who didn't vote in the election and take the log of it. And this allows you to constrain the proportion between 0 and 1. And we know that you can never have a proportion larger than 1. That's more than 100%, right? That's more than everybody. So taking the logarithm constrains it within that range, bounds it within that range of 0 and 1, and provides you with a really good interpretive model as well. So no matter what the values of the independent variables will be, or their coefficients, the predicted value of Y will always be between 0 and 1. And people either voted or they didn't, right? They either voted yes or they didn't no, and that 1 is yes and 0 is no. And how do we interpret that though? So running the log using logit transformation for a dependent variable that is constrained in that 0, 1 allows us to talk about odds and probability. So we can talk about it as the odds or likelihood change. So the greater increased likelihood that someone would vote in the previous election based on factors like education or occupation or employment status or gender, right? So that additionally, you can see how that would make sense. So we'd be able to want to say that each additional year of education, as an example, or a year of schooling, as in the previous example, increases the likelihood or the odds that someone voted by a certain amount, right? So you can understand why taking the log of your dependent variable, when you're talking about something that is dichotomous, like you either voted or you didn't, becomes a useful model. And that gets referenced again in chapter 9 when he's talking about logistic regression, which is what this actually is. This logit transformation is logistic regression. Polynomial models. The quadratic model we've already kind of talked a little bit about. It is connected to the logarithm of it, and cubic models are the most common. So what we're essentially doing is we are squaring or cubing our independent variable values. And why are they popular? Because sometimes functions are nonlinear. They can also be used with any kind of quantitative variable rather than only ones that are measured at the ratio level. We've never worried about this. We've treated interval and ratio variables as the same. But running polynomial models allows us to deal with those variables that maybe don't have absolute zeros or arbitrary zeros or have to be positive or are dealt with in that way. We can also sometimes use it with ordinal level variables if we have enough response categories. So if we have 5 response categories, we've talked about this before, you can treat 1, 2, 3, 4, 5 if they are ordinal. So polynomial models are useful when we are dealing with those kinds of variables as well. And they allow us to deal with predictable curvilinear relationships that can be expressed with those polynomials. Quadratic equations provide us with parabolas. Logarithmic functions provide us with curves that rise steeply at first and then sort of taper out, level out. Cubic models are almost like S curves because they go up, down, and then back up again. And so we can see how there aren't a whole lot of cubic or beyond things in sociology, right? We don't have a whole lot of variables that are going to wiggle that much along the axis in terms of their relationship. But we do have a few things that can be best expressed, at least in the portion of the data that is available, with something that is more linear, even if we don't get in the bound of the data to that full turn in the model, in the way that it would graph. Allison includes several examples illustrating how quadratic, cubic, or polynomial functions graphs differently and more accurately than simple linear functions. For the most part, we haven't been worrying about that differences between interval and ratio level variables. But he points out that when we don't have a true zero, these models may do a better job of estimating the true parameters. So a simple quadratic function, this could be miles driven per year in somebody's lifetime. We're likely to see this as a parabola, right? The data goes up and then it turns down. This is squared, right? So it goes up to a certain point and then it goes back down again. So we know this is likely to be nonlinear. You don't drive until you reach your teens, right? And then you may drive a lot until you reach a certain age, and then you may drive very little after that. The older you get, as you reach retirement, you no longer need to go to work, you don't need to commute, you have less driving, right? Or maybe health issues as you age make it less likely that you drive, or you drive fewer miles a year. So we might expect the curve to look like a parabola.